So we had to come up with another equation, okay? This one's called Goldman-Hodgkin's-Katz equation. And now we have to consider the potassium and the sodium and the chloride all at the same time. And there's a very important point right here on the top in front of every single one, okay? It's a P, and the P stands for permeability. So just like the man in the video was talking about those leak channels that let the potassium leak out, okay? There isn't any leak channels for sodium, okay? Which means that the permeability for the potassium to move is much greater. So you saw how close it was to the line on the potassium. Potassium is still the biggest influence. So when we look at that, we can say that the K compared to the sodium, compared to the potassium, is 50 to 1 to 10. So you can either put a 50 in front of each one of these and a 1 in front of each one of these and a 10 in front of each one of these, okay, when you're figuring this out. Or if it's easier for you, you can bring them down and it's the same ratio, but it's much smaller numbers, okay? So you can say, well, okay, we're going to make the K a 1, we're going to make the sodium a 0.02, and make the potassium a 0.2, okay? Same numbers, just smaller. Make it easier for you to deal with, okay? So in each case, you would have to know the concentrations on the outside and the inside, outside of the inside, and oops, inside over outside, just like on the Nernst equation, in order to figure out what that's going to be. So I never did find a good video for explaining Nernst equation to just figure it out. But this one does the Goldman-Katz. This is not actually used in a human cell, so they've got a little bit different numbers, but you'll still get the right idea. Oops. Come on.
Okay, I want to talk about another equation that's really important when you're discussing permeability of membranes and such, and that's the Goldman-Hodgkin's-Katz equation. This is a little bit of a background thing I did here, just to kind of give you an idea of where this came from and why they chose to create another equation, because we had the Nernst equation, which was really useful for calculating the equilibrium potential for a particular ion. But there was a little more to it than that when they started doing some experiments, and a lot of these experiments were done with what was known as the squid giant axon. It's just essentially a really big axon that you can really work with on almost, on a larger scale, so it's not really small and really difficult to work with, so it's very very beneficial. Initially, it was believed that the neuron was only permeable to K+. Okay, so we only thought initially that it was permeable to potassium. It was determined by experiments with the squid giant axon that the resting membrane potential did not equal the Nernst potential for potassium. So what I'm saying here is that if it were true that the neuron were only permeable to potassium, then the resting membrane potential, which we abbreviate as VM, would equal the Nernst potential. But it didn't. When they did the experiments, it didn't work out. So the conclusion that they came up with was that this means that the membrane is permeable to other ions. So there's several other ions, obviously, but again, the important ones were sodium and chloride. So there's other ions that this axon or these neurons are permeable to, or the membrane is permeable to. So to model the complex movement of ions, an additional equation was used called the Goldman-Hodgkin-Katz, or GHK equation. And if I could get it on here, I'll tell you what it is. So essentially, this is the resting membrane potential is equal to 58. This is the abbreviation for, R for the gas constant and temperature and Faraday's constant and whatever else. This is an easier way to remember it. So the VM is equal to 58 log of the permeability, these P's here in front of each of these values is a permeability. So this is a permeability constant, what's known as a permeability constant for each ion. So it's 58 log P of K, so permeability of K, and this is the concentration of potassium outside plus P for Na, so permeability constant for sodium, the concentration of sodium outside the cell, plus P plus the permeability for Cl multiplied by the concentration of chloride inside the cell. So the big difference is this is inside the membrane, this is outside, okay? And the same thing on the bottom here, this is permeability constant for potassium, concentration of potassium inside, plus the permeability for sodium times the concentration of sodium inside, and this is the permeability of chloride times the concentration of chloride outside, okay? So it's a long equation, it's a bit complicated, it seems a bit complicated, but it's really not. It's actually quite easy to use. So I think we have enough time to look at a problem. So here we go. For the next set of problems, assume the cell has the following intracellular and extracellular ionic concentrations. Okay. So we go here and it says the cell is permeable to potassium, sodium, and chloride. However, it is not equally permeable to each of the ions. The ratio of permeabilities for K, Cl, Na+, and Cl- respectively are 1, 0.5, or 0.05 rather, 0 and 0.43. So what is the resting membrane potential for the cell? So this is a great little question. It really will solidify what I just said about the Goldman-Hodgkins-Katz equation. So they want to know what the resting membrane potential for the cell is, and they've given us the permeability constants, 1 for potassium, 0.05 for sodium, and 0.43 for chloride. And they've also given us all the values for the intracellular and extracellular spaces. So what's going on inside the cell, what's going on outside the cell, okay, for each one of these ions. So let's just write down what we need here. So I will say membrane potential, resting membrane potential is equal to 58 log. So that's all the same. Now we need a pretty long line here, so we got a lot to write. So let's look first at the permeability for K. So, okay, the permeability for K is simply 1, according to this paper. So, I'll just plug in a 1 here. So that's just 1. And we'll look here at the concentration outside. So the concentration outside the cell is 15 millimoles, right? So I'll plug in a 15 here, so this is multiplied by 15. Now I'll do the same thing for sodium here. Okay, so this is 1, sodium is 0.5, so 0.05, and I want to multiply that by the concentration of sodium outside the cell here, so that's 170 millimoles, so see, extracellular, outside the cell, 170, so I'll plug that in here, and I'll say that's plus the last part, so 0.43 for Cl-, okay, that's the permeability constant, so it's 0.43, and that's going to be multiplied by the inside for Cl, so that's 9. Okay, so we're just going to plug a 9 in, just like that. I'll do the same thing down here. So again, the permeability constant remains the same for all of these. That's not going to change. But now we want to know what the potassium concentration is inside the cell, and that's 440. Okay, so this gets 440, and that's plus the same 0.05. And let's see what Na plus outside the cell is, or inside the cell rather, is only 15 here. Okay, so say 15, and this is still the same permeability, so 0.43. And now I want to know what Cl is outside. So it's 130. And the only reason you reverse so this is Cl inside the cell first and then Cl outside the cell, the only reason you do that is because of the negative. We're not using those Z over here, so we have to reverse these in order to get this to come out properly. So with all that plugged in, you can, I would probably recommend that you do it in pieces. So you would start maybe with just calculating what this top value is here. So I'll start with that. So it's 15 plus 0.05, and that's multiplied by 170, and that's going to be plus 0.43 multiplied by 9. So the whole top value is about 27.37. So 27.37, right? And let's see, the bottom is 440 plus 0.05 times 15 plus 0.43 times 130, and I get 496.65. So I'll plug that in, 496.65. Now I'll just add my 58 and the log and the membrane potential there, resting membrane potential. So the VM is equal to, let's plug it all in, so 58, and that's going to be log 27.37 over 496.65, and that equals negative 73 millivolts. Okay, so resting membrane potential here is negative 73 millivolts, and that's pretty consistent with what they got in a lot of the cases when they were doing these experiments. They were getting somewhere around negative 75. So that would be how you would use the Goldman-Hodgkin-Katz equation for a problem. It's pretty simple, plug and chug.
So, you can always go back and take another look at this. If you have any problem doing your homework. Okay. Okay, so there's your homework. Which means, told you there's just a couple times you have to do math. This is one of them. Okay, so this is going to talk about a mammalian skeletal muscle, a human red blood cell, and the squid giant axon. The one he was just doing is the squid giant axon. You saw that giant sodium number. Squid, of course, lives in the ocean, right? Okay, so that's where you're going to get that. See this Nernst potential number over here? You do not need that for your calculation. It's just there so that you knew what it was, okay? What you're going to be using is the inside and the outside. And you are going to use the permeability that we came up with. Did you notice he used 58 instead of 60? That's because 60 is just rounded. It's just rounded up to 60. So here's what you're going to use, 58 times the log. Okay? And you have basically 3 problems to solve. Okay? So that's what you're going to be turning in next week. You can turn it in after your test, but you can assume that you will need to know this for your test. Okay? Okay. We have a whole nother PowerPoint about the action potential, so we're going to take a 10-minute break now, and then we'll come back and we'll finish the information on the action potential. So everything we have talked about today and previous to this has led up to this one point, which is that we are going to talk about what an action potential is and what an action potential does inside the cell. So one of the things to keep in mind is that when we talk about the electricity inside of a cell, we are talking about millivolts, okay? 1,000 times less than a AA battery, okay? So a AA battery has a 1.5 volts, and we're talking about millivolts, okay? So we're talking about extremely small amounts of electricity, okay? So what happened was these two guys, Hodgkins and Huxley, and if you do anything that has to do with the nerves, if you become a neurologist, you'll probably have another class that covers electrophysiology, which is the measurement of these of these impulses inside the body for a variety of reasons. And then you'll hear more about these two guys who are the ones that received the Nobel Prize for being the first people to ever record the action potential inside of a cell. And they recorded it in the one that he was talking about in the video, which is called the squid giant axon. So this thing inside the squid is huge. It runs all the way down the tail, and it's very big, and it was big enough that they could actually physically see it without a microscope, and it was also big enough that they could actually put electrodes into it. They started doing this in the 1940s. So if you think back, you've probably seen pictures of like old surgical instruments. And if you think about the things that they used to be able to do, they didn't have anything very small or very fine. So they had to work with big, bulky equipment, and they had to be able to find an axon that was actually big enough that they could actually record from it with these great big giant electrodes, okay? Now all the stuff is much, much, much smaller, and we're using microscopes to find the cell and to penetrate the cell so we could get the recordings. But they had great big giant stuff that they had to use, okay? So when you record from a cell, you've got to have a couple of components, one of which is you have to have something that will record inside the cell. You also have something that's called an oscilloscope that is going to show you the movement of the ions inside the cell. So basically this is just showing you the movement of electrical ions, either pluses or negatives, going up and down, okay? You also have to have an amplifier, because if you're talking about a millivolt, then you've got to be able to have a way that you could actually make it show up. So that's the other part of this, is an electrical stimulator and an amplifier, and then something so that you can actually see it. So when they first started tracing the action potential, this is what they saw. And what they saw was that membrane, remember the one with the flat minus 70? That resting membrane potential changed. And the resting membrane potential went way up above the zero and came way back down. And it did it very fast. Okay, this is milliseconds. Okay, so this is milliseconds, and what we saw was these big ups and downs that went on inside of the cell. Okay? So we have to learn some nomenclature, and we have to learn some more things to remember. We said that the equilibrium for sodium was up here. The equilibrium for potassium is down here. RMP stands for resting membrane potential. And then we have this other little thing we have to introduce, which says threshold for impulse initiation. Okay? So, you also saw that picture went way up and went way down. So we have to have names for all that. Okay, so this is the resting membrane potential. When we start to go up, it's called depolarize. Okay? Depolarize is when we start going up from the resting membrane potential. Okay? And then you saw that it kind of turned over and came back down. When it turns over and comes back down, then we call it repolarize. Okay? We call it overshoot. When it goes over zero, that's called overshoot. You'll see here it says reversal of membrane potential, but we don't actually use that as a term very often. So overshoot, we're going to depolarize, we're going to overshoot, we're going to repolarize and come back down. And then what often happens is it goes under the resting membrane potential, and that's called hyperpolarize. Okay? You'll also notice that there's two constants here. We always have the time on the x-axis, and we always have the millivolts over here on the y-axis. Okay? Okay. So, the action potential, what is it doing? It's actually carrying a signal. It is passing on information. It's passing on information from a nerve to a muscle. It's passing on information from one nerve cell to another nerve cell inside your brain. Most of you probably know, if you had anatomy, that the vision cortex is at the back. Okay? Okay? Well, you know what? If you're processing information and it's visual, you got to get that information up to the front, right? Okay, that's nerves. That's neurons. They've got to move it along. This kind of processing is very, very fast. Like I said, milliseconds. Okay? So we are talking some very fast processes, which of course you know, because if you're trying to calculate in your head, you know how fast that can be. You look at somebody, you recognize them, yes or no, okay? It's very fast. The other thing is that we have voltage-gated channels that are in the membrane. Voltage-dependent channels in the membrane are responsible for the action potential, okay? Voltage-gated means that a change in voltage will make the channel open, okay? Voltage-gated means a change in the voltage will make the channel open, okay? So it's going to be sitting there at rest. It's not going to be doing a whole lot, but maybe a more negative or a more positive change in the membrane potential is going to make the channel open, okay? The other thing to remember is this is all or nothing, okay? Very important, all or nothing. It's a have or a have not. You either have an action potential or you do not have an action potential, okay? There's no such thing as a little action potential and a big action potential, okay? There's only one size, an action potential, okay? So, the other thing is it's going to stay consistent. When you took the anatomy class, you probably found out that you've got nerves that start in your spinal cord and it goes all the way to your bottom of your foot. So that means the axon, the part that's carrying the message, has got to go all the way from your spinal cord, all the way to your foot. You know, that may be 2 feet or 3 feet, or, you know, you're getting close to a meter. Some basketball player, it may be a lot longer than that, okay? It's got to carry the message all the way down to the toes so that they wiggle, okay? And when that happens, it's because of the fact that the action potential is going to stay the same size the whole length of the nerve to the muscle, okay? So it's going to stay the same size. It's not going to wear out and stop halfway down, okay? So, action potentials occur all over your body for different reasons. They occur inside your brain. These are neurons inside your brain. They occur at the neuromuscular junction where the nerve tells the muscle what to do. And they also occur in your heart because your heart can pump all by itself even without any messages from the brain. Okay? So, what happens? How do we get this action potential? How do we change that cell that is at a resting membrane potential? How do we change it so that it has an action potential? And what we do is to change the permeability of the cell. Okay? And how we change the permeability of the cell is first by opening a ligand-gated channel, okay? So that means that some ligand is going to come land on its receptor, and that receptor, which we've already talked about, is going to change the information inside the cell. In this case, it's going to change and open a channel, okay? There's a set of channels called GERK channels. G-coupled protein, inward rectifying potassium channels. Okay, that's what that stands for, GERK. In other words, it is a channel that is hooked up to a receptor. We already learned all about receptors. Now we are learning about the channels that go next to them, and we are going to open those channels. A neurotransmitter can open a channel, okay? So first you have to have the neurotransmitter open the channels, and the channels are small, and they just leak in a little bit, okay? They put a little bit of sodium into the cell, okay? So these are sodium channels. These are ligand-gated sodium channels, okay? And they are going to make a little bit of a stimulus. And then, if there's enough stimulus and we reach threshold, then we get a voltage-gated channel, okay? Because there has to be enough change in the membrane potential in order for the voltage-gated channel to open, all right? So, let's take a look at how this works.
Hello and welcome to Interactive Biology TV, where we're making biology fun. My name is Leslie Samuel. This is episode 13, where we're going to be talking about the action potential. I'm basically going to be giving you a review of the concepts that we've been talking about up to this point when it comes to the action potential. Over here, we have our neuron. And the part of the neuron that we are going to be focusing on is the axon. So that's this region here, starts here, and it goes to about there. Now what I'm going to do is I'm going to take a section of the neuron. So let's say I'm going to take this part here, and I am going to draw it down here. So here we have the axon. This is inside the axon, and this is outside the axon. Now, if you remember from a previous episode, outside the axon we have a lot of sodium ions. So I'm going to draw sodium ions here, and they are all outside the cell. Now let's look over here. Here we have a stimulus that's happening, and you can see there's a first stimulus that does not reach threshold, so nothing happens. Another stimulus comes, it does not reach threshold, so we still do not get an action potential. If we have a stimulus that's strong enough, and I'm going to draw another stimulus in here. So let's say we have a stimulus that's that big. That's going to reach the threshold and cause an action potential. When that happens, voltage-gated sodium channels are going to open, and that's going to cause sodium to rush into the cell. Of course, that's going to start at the axon hillock. Sodium is going to rush in, making the membrane potential even more positive, causing more channels to open, more sodium to rush in, more sodium to rush in along the axon. What is that going to do to the membrane potential? You can see right here, this is where we get depolarization. The membrane potential goes up and up and up and up, and it's trying to reach the Donnan equilibrium for sodium ions. And that equilibrium potential is somewhere around 58 millivolts. So sodium is rushing in because of the driving force causing sodium to go in. Sodium wants the membrane potential to go up to its Donnan equilibrium, and that is around 58 millivolts. At this point, voltage-gated potassium channels have enough voltage in order for them to open. So I'm going to erase all of this now, and we're going to take a look at the axon again. I'm going to draw it here in blue. And inside the cell, we have a bunch of potassium ions. Now we have such a positive charge on the inside that potassium ions want to leave because positive repels positive. When voltage-gated potassium channels open, potassium can now leave the cell. So we have a lot of positive leaving the cell. And what that is going to do is cause repolarization where the membrane potential is going down. Just like with sodium, Potassium wants to reach its equilibrium potential, which is somewhere around negative 93 millivolts. And that is why the membrane potential is going down as it's leaving, because potassium wants the membrane potential to be at negative 93 millivolts. That is where it is most comfortable. Considering that the resting membrane potential is around negative 70, the membrane potential goes significantly lower than that negative 70, and this phase we call hyperpolarization. All along this process, we have the sodium-potassium pumps that are pumping sodium out of the cell, 3 sodium ions out, and 2 potassium ions back in. And that's going to cause the membrane potential to eventually reach back to its resting state. This is the entire action potential, looking at depolarization, repolarization, hyperpolarization, and it getting back to the resting state. I hope that makes sense. If you have any questions, feel free to leave them in the comments below. I'd be happy to answer your questions and maybe even make a video answering your specific question. That's it for this video, and I'll see you in the next one.
Okay, so we are going to be drawing an action potential, and I've just put this up there because I wanted to be able to make sure that you could see something. This is what you need your paper for today, and you need to draw this now. So if you don't have any paper, you can come up here and get paper from me so that you can put it down. I have put this on every test I have ever given, including every final. Okay, so I just gave you a big hint. Okay? I wanted to remind you that if you want the PowerPoint in advance, I give it to the 2 class monitors to post for you guys to see it. This is not the videos, it's just the PowerPoint. But if you'd like me to send it to you specifically, just send me an email that says I would like the PowerPoint in advance, okay? And I'll add you to the list, okay? All right. You are going to need this again in just a couple minutes. So make sure that you make it big enough that you can add information as you go. Okay. Please make sure that you label your access. I do take off on a test when you don't. Okay, you're going to have a resting membrane potential at 70. Okay, you are going to have a threshold about 20 millivolts higher than the resting membrane potential. So I put minus 50, okay? Minus 50. If you draw me an action potential and your threshold is lower, okay. If you draw me an action potential and you put the threshold below the resting membrane potential, you are going to lose points, okay? The threshold is always 20 to 25 millivolts higher, okay? So if somebody's dealing with some crazy cell that has a minus 90, you still know the threshold is going to be about 20 to 25 millivolts higher, okay? So that's where your threshold is. What does threshold mean? Threshold means that the voltage-gated sodium channels are going to open. So the way you get from here up to here is the stimulus-gated channels, the ones that might not stimulate enough, okay? The ones that you have to wait on, okay? These are the ones that hook up to the receptors. So first you have stimulus-gated channels, and then you have voltage-gated channels, okay? And all of this is sodium going into the cell. So over here on this side, make yourself a little note. This is sodium in, okay? This is stimulus-gated channels right here. Stimulus-gated channels start first, okay? Once you get over 0, remember that you are now at overshoot, okay? Okay? And you are probably not going to make it all the way to plus 55. Usually you're going to get up someplace like plus 40. Okay? The reason that you're not memorizing specific numbers for this is because it's the concept. You know it's going to be different depending on the kind of cell, but you still got the concept. You know it's going to go over 0. You know it's going to go up towards the sodium equilibrium. And now it's going to come back down. Okay? This is repolarize. Okay? And the reason you are repolarizing has to do with the fact that you are now letting potassium out of the cell. So this is K out. Okay? Potassium out. Potassium goes out of the cell during repolarization. Okay? When it comes under the resting membrane potential, it is hyperpolarized. Okay. And when it comes back up to resting membrane potential, that's because of the sodium-potassium HPAs. Okay? That's not actually on the picture, but that's just why it goes back up. So it's going to hyperpolarize, and then it's going to go back up to the resting membrane potential. All right? Sodium in, potassium out. Okay? Okay. Now, if you look at this picture over here on the other side of you, you'll see a couple more things that are written on there. One of the things that you're going to see is up here at the top. It's going to say voltage-gated sodium channels open, and it's going to say voltage-gated sodium channels close. Okay? We've got a couple more slides that are going to talk about how those channels close. But when I usually ask for this on a test, I also ask for you to put in where the channels open and where the channels close. Okay? If you tell me that voltage-gated sodium channels open here, that's wrong. Okay? Voltage-gated sodium channels open at the threshold. Okay? So this is open sodium. And right here is closed sodium. Just like over there on the picture, okay? And at the time that the sodium channels are closing, then you also have the potassium channels opening. Okay? The potassium channels are going to open. If you look over here on this slide, it has it all nice and marked for you. But basically, right up there at the top is where those voltage-gated potassium channels are going to open. Okay? Now, here's another thing to think about. Where are the potassium channels closing? They're closing down here. Okay? They're closing at the bottom. Not at the resting membrane potential, but at the hyperpolarization stage. Okay? So when you get to your lowest point and it starts to go back up, you have closed your potassium channels. Okay? K close. All right? So the way I usually word this question on a test is I give you a list of things you have to mark. So I will say, please draw an action potential. I want you to label, where the channels open and close, where's the repolarization, where's the depolarization, where's the hyperpolarization. And what happens is, if you add up all this stuff, depending on what I ask for, you're looking at a question that's worth 10 to 14 points. Okay? So now, you all know that, and you're going to do great, right? But that's the point of actually drawing it for yourself, is so that you will remember where all the things go. Okay? Does this seem to make sense to everybody? Okay. And you have this nice spot over here where it tells you where everything goes. So here's a really good slide to look at when you're studying. Okay? All right. So this is a picture of what looks like a drinking glass, but it's really a glass pipette, a giant glass pipette. And it's measuring the sodium channels on the membrane of a cell. I guess it is on. Okay. It's measuring the sodium channels inside the cell, okay, right there on the cell membrane. And when they did this, what they found out was